Now we can calculate the kinetic energy of the 50-gram mass at 20 centimeters from the axis using the moment of inertia, I equals mr squared, mass being 50 grams, r being a 20 centimeter distance from the axis. Calculating this, we get 20,000 grams centimeter squared, which is 0.002 kilogram meter squared, a gram being 0.001 meters, a centimeter being 0.01, a gram being 0.001 kilograms, a centimeter being 0.01 meters. If we replace gram and centimeter with those quantities, be sure to square the centimeters, we end up with this result. At 5 revolutions per second, then, well, 5 revolutions per second, each revolution is 2 pi radians, we get 10 pi radians per second. Our kinetic energy is then 1/2 I omega squared, 1/2 our moment of inertia, 0.002 kilogram meter squared, multiplied by the square of our 10 pi radians per second. Multiplying that out, we get, I'm not going to read, well, yeah, the square of 10 pi is 100 pi squared. That's radians squared per second squared. Multiplying each of these meters by a radian, we think of that as a meter of radius by a radian gives us a meter of arc length, and we get the radian times each radian times each meter gives us a meter of arc length. So we get meter squared out of the meter squared times the squared radians. We get a second squared in the denominator times a kilogram. Kilogram meter squared per second squared is a joule, so we get approximately 1 joule when we complete the calculation. And this completely agrees with the calculation we made previously based on the speed of the 50-gram mass as it moves around this circular path. And this reinforces the idea that the kinetic energy is I omega squared. If you think deeply, somewhat deeply, about the relationship between this calculation and the previous calculation, you'll see that this calculation incorporates the previous calculation, because previously we did multiply the meters of radius by the meter of radius multiplied by the radian of angle to get the meter of arc length. The only difference is in this calculation, that calculation was essentially included when we did the mr squared to get the moment of inertia. So you maybe want to think clearly about the relationship, the comparison between this calculation and the previous one, and maybe derive a little bit more insight. However, if you just know this, you're doing pretty well.